All right, good morning, everybody. We're going to talk about the integral test for convergence today. In the first video here, it's going to kind of talk about the idea, get an understanding of why it works, and then in the next video, we'll do a few examples together. Okay, so yesterday we talked about some different series, one of which was the harmonic series, summation of 1 over n that we kind of see right here, okay? What did we say? Well, we said that it was divergent. All right, so now it's time to prove the statement. This proof will also get us started on the way to our next test for convergence that we'll be looking at. So we're trying to prove the harmonic series, once again, summation n goes from 1 to infinity of 1 over n, is divergent. Okay, so we'll start this off by looking at an apparently unrelated problem. Let's start by asking what the area under the function f of x equals 1 over x on the interval from 1 to infinity is. All right, so this is something we looked at when we did integration. That's an improper integral because we're looking at the area as it goes to infinity. And we saw that that went off to infinity, and we said that that area diverges, okay? So, just how does this help us to prove that the harmonic series diverges? Well, recall that we can always estimate the area by breaking up the interval into segments and then sketching in rectangles and using the sum of the area of the rectangles as an estimate to the actual area, right? Our Riemann sums. Let's do that for this problem and see what we get. We're going to break up the interval into subintervals of width 1, and we'll take the function value at the left endpoint. So we're going to break this up doing a left Riemann sum with widths of 1. So here's what that would look like. So here's the 1 over x function in red, okay, and on the interval from 1 to infinity, all right, and we're doing left endpoints, okay. So there's the rectangles, nice widths of 1, and then if we look at this area formula down here, okay, the numbers in the first parentheses are the heights. So the heights, for example, the first height is going up at x equals 1. And remember, the function is 1 over x. So that would be 1 over 1. The height of the second rectangle would be 1 over 2, 1 over 3, and so forth. Okay? So first numbers in each product represent the height, and the second number, the 1 in the second parenthesis in each product, those are our widths of 1. Okay, each of these is a width of 1. Okay, so there's our approximation, which goes on forever. But if we clean this up a little bit and do the math, I mean, this is just 1. This is 1/2, 1/3, 1/4, 1/5, so on and so forth. Okay, so that's this line. And then, well, if you think about it, well, we could actually write that as this series. Okay, so using a left sum to approximate the area, what we end up with is our approximate area is going to be an overestimate. We can tell because the rectangles are above the curve, okay? So the area here, which can be represented as this thing, is going to be an overestimate. So it says, now note a couple things. First, each of the rectangles, again, overestimates the actual area. And secondly, the formula for the area is exactly the harmonic series. Putting these two facts together gives us the following. The area, which is approximated by this series, is going to be larger in value than the actual area under the curve. Right? Well, if we know that this thing actually goes off to infinity, and our approximation to the area is going to be even bigger than that, then we've just shown that this series has to diverge, right? If this integral goes off to infinity, and we've shown that this is going to be larger in value than that integral, then by comparison, basically, this thing is also going to diverge, okay? So that's part of it, all right? Now, yesterday, I talked about how the p series, 1 over n to the p power, will converge if p is greater than 1. So here's an example, 1 over n squared. The claim is this will converge, okay? But again, let's try to see, you know, with an integral and with a graph, what's going on here, all right? So we're going to do something similar to prove, to the above process to prove this. We will try to relate this to the area under the graph of 1 over x squared on the interval from 1 to infinity. So again, something we practiced back in the day in class, and go back in your notes, we showed that this integral actually equaled 1. Okay, so we're going to keep that kind of in the back of our minds for a little bit. All right, we know that this thing equals 1. So we're going to try to estimate the area under this curve. We will do this in an almost identical manner as the previous, with the exception that this time we're going to use right endpoints for the heights. Okay, so we're going to use a right Riemann sum on this. So here's the function 1 over x squared. All right, and there's our rectangles we're setting up with widths of 1 again. Okay, so again, the first height is at 2. So the height would be 1 over 2 squared. That's that number you see there. And then there's the width of 1. So there's the area of that first rectangle. That would be 1 over 3 squared for the height times a width of 1. So there's the area of the second rectangle, and then so on and so forth. Okay. This time, unlike in the first case, the area will be an underestimation of the actual area. And the estimation is not quite the series that we are working with. Okay, notice this is what we've gotten back when we've cleaned it up. If we go back to the original series, okay, this is what we're talking about, the series of 1 over n squared as n goes from 1 to infinity. If we actually start expanding that out, we get this, okay? Well, this portion of it is our area estimation from above, okay? So the only difference between our area estimation and what this actual series is this first term. And if you clean that up, that's just the number 1. Okay, so we get 1 plus our area approximation. All right, well, that leads us, and again, that area approximation is less than the actual integral value. So that's what's going on over on this side of the inequality. Okay, that's the 1 that we cleaned up, that's that, and then our area approximation was to this integral. All right, but again, the way we set this one up, that area approximation is actually less than the integral value. All right, and we know that that integral value equaled 1. That's what I said, remember, for a moment from way up here. Okay, and so in any event, putting all this together, right? So here's our series, okay, which is 1 plus the area approximation. Well, this thing approaches 1, and so at the end of the day, this series, which is less than all this stuff, is less than 2. All right, so putting it all together, we see that this series, even though it keeps adding up forever, is going to add up to some number less than 2. All right, so we've basically just shown that that converges. Okay, so what all this really boils down to in terms of the integral test is the following. Okay, there's a fancy proof, down at the bottom here. It's it's a little tricky to read through, but it basically formalizes what we just talked about above. Or basically, the big idea is this. If we have a function that we know either converges or diverges, we could set up, some sort of Riemann sum to show that that thing is also then either going to over or under approximate and thereby converge or diverge by comparison. And that particular Riemann sum could represent a series. All right, so at the end of the day, what it all boils down to is this, okay? Suppose that we have a function that's continuous, positive, and decreasing on the interval from k to infinity. Okay, the idea is that it's above the axis, and it can go up and down, but at the end of the day, the thing's got to be approaching the x-axis, all right, on some interval from k to infinity. And all that means is that as we go further out to the right, that amount of area is going to approach 0. Okay, so that kind of opens the possibility for convergence here. All right, so the condition is we have a function that's continuous, positive, and decreasing on the interval we're working over. And we can find a way to represent our series as a function that we can integrate. And the gist is this. If the integral version of our series converges, then so will the series itself. If the integral version diverges, so will the series itself. All right, and this is why it's called the integral test. If we have a series that can be rewritten as a function that we can integrate, and then integrated as an improper integral, we can either show that that integral converges or diverges, then the same is going to apply to the series. Okay. Now, it should be noted that whatever value the integral converges to, that is not what the series itself converges to. The series would converge to some value a little smaller. Okay, so it's not giving us the value of convergence, but by comparison, if one converges, so if the integral converges, the series will. If the integral diverges, the series will as well. Okay. So again, a little bit tricky, but let's run through some examples. And again, if you want to, go to the link that I've provided and scroll down and look through the proofs and stuff, basically, again, just formalizes the ideas that we went through with 1 over x and 1 over x squared, okay? But this is the gist of it. If we integrate and the integral converges, we know the series does. If the integral diverges, we know the series diverges as well, okay? So we'll practice that in the next video.